study will be about learning the value of the offline optimizer, something we really didn't initially consider when using this software. But as we started to, take a deeper dive into it, we saw this feature and thought that it sounded appealing to use. So we tried it on one of our ethanol fermentation processes. So the fermentation process is essentially a series of large tanks where we use yeast to ferment sugars into ethanol. The front end of the fermentation process is fed with mash, which contains the fermentable sugars and light steep water. We have a residence time through this process of about 40 hours. So our goal was to take these flows into the different tanks on the front end of the process and be able to predict what the final conversion would be. So as you can see here in the top left plot, that we were able to get a pretty good model. R squared of about 0.62, which is excellent for this type of exercise. And the other thing that the software allows us to do is it shows what are the key variables in the model. So in this case, we're able to see that the mash flow to the pre-fermenter is the most important variable to the model. So this is great, right? We're able to predict conversion based on what's happening at the front end of the process. But what do we actually want to do, right? We want to maximize conversion. So how do we do that? What do we have to change in order to achieve maximum conversion? Well, this is what the optimizer allows us to do. So the way this works is you can define different cases. So in this case, we are defining cases based on what we're feeding into the process, right? What our mash feed flow rate is. After we do that, we are simply setting our goal for the Y variable, which in this case is to maximize conversion. Now, one of the most important points here is that that's literally all you have to do, because the solution that the optimizer gives you is going to be constrained by the correlation structure of the data. It's based on how this process has been ran for however long the data set goes back. So what we can see here is that for mash flow to the pre-fermenter, the optimizer is calling for more mash flow. But of course, to get a complete solution, we need to look at every variable at the same time, and what that tells us is exactly what we need to do. So more mash to the pre-fermenter, take some away from fermenters 1, add a little more to fermenters 2, add some more light steep water, and we're all doing this at a fixed total mash flow, which was the only constraint that we put on the system. So again, the optimizer ensures that the predictions remain substantially within the correlation structure of the model. It's interesting because this solution was actually confirmed by the opinion of the plant experts, but it's difficult when you have so many different levers to pull to determine exactly what the right combination is, and that is what the optimizer allows us to see all at the same time. So this test actually did validate our belief that using historical data will provide us additional insight in the optimal way to run our processes. So where we see value in the optimizer, as the previous case study just went over, we believe it can help us improve our yields. We also believe it can aid in faster development of new products in research and development, faster implementation of those new products in our production plants, and finally applying design of experiments in our daily operations to reduce costs and improve product quality. There's probably more. This is just the short list that initially came into our minds.